For decades, the standard model of cosmology has operated on a specific premise. The universe's expansion is governed by a single, unchanging rate. For nearly a century, the goal of astrophysics has been to calculate this expansion rate as an objective, universal number, measured from standard vantage points. The model relies on the existence of a constant vacuum energy, often called lambda, which acts as a uniform engine driving the universe apart. Modern astrophysics assumes this vacuum energy is absolute, meaning it should appear identical to every observer, regardless of where or when they are looking. However, our two most precise methods for measuring that expansion now directly contradict one another, a conflict known as the Hubble tension. By analyzing the ancient plasma of the early universe captured in this map, the Planck collaboration calculated an expansion rate of 67.4. But when we look at the late universe using modern supernovae, the SH0ES collaboration arrives at a significantly higher rate of 73.0. These two figures are separated by a 5 sigma gap. Their error margins do not overlap, meaning they are mathematically distinct. After a decade of independent checks, the gap has only widened. Technological improvements have ruled out simple calibration or measurement mistakes. The persistence of this discrepancy suggests that the standard model's assumption of a perfectly uniform universal constant may be incomplete. ODTOE addresses this by shifting focus away from macroscopic empty space and plunging down into the subatomic environment of configuration fields. In this framework, dark energy is no longer viewed as a constant force inherent to a vacuum. Instead, ODTOE identifies specific microconfigurations, called parent-protons, as the primary carriers of mass energy within these fields. These parent-protons undergo constant microscopic mergers. Accelerated expansion is actually the statistical byproduct of these collisions. Because this merger rate is tied to the local environment, it fluctuates based on the density and structure surrounding the parent protons. Expansion is therefore not a property of space itself, but the active, cumulative result of these subatomic events. This leads to the theory's central mechanism. The expansion rate and observer measures is weighted by the structural coherence of their specific era. Measuring the early universe means averaging data across a high-temperature, low-coherence plasma, resolving mathematically to 67.4. But the late universe is a high-coherence environment, anchored by organized galaxies. Sampling this structured era resolves the same physics to 73.0. The observer's epoch determines which version of the effective expansion rate they are able to sample. The exact mathematical difference predicted by these coherence weights matches the 5 sigma gap currently observed in the Hubble tension. Seen through this lens, the two values are no longer a contradiction, but a predictable result of measuring the universe at different stages of organization. Skeptics might argue that this is simply a variation of modified gravity. However, modified gravity models typically apply a single, universal correction that remains the same for every observer. ODTE is observer-indexed. It predicts that two observers using different ways of aggregating the same data will measure different expansion rates based on local coherence. This is testable. Light from standard candles should show systematic redshift changes, depending on whether they are in dense galaxy clusters or empty voids. We should also see small directional dependencies in the expansion rate that align with the universe's large-scale structure. Recent sky-binned data from our most advanced instruments is already showing hints of these directional variations. If these predictions hold, then 67.4 and 73.0 are both correct. The Hubble tension is not a crisis, but the proof of an observer-indexed universe, where our vantage point shapes the reality we measure.